Chapter 2, AP Environmental Science, Matter, Energy, and Systems should be more or less a review of chemistry and basic scientific method principles. So let's do this. Back in the 1960s, there was a Hubbard Brook experiment in the forests of New Hampshire. This was a very large-scale experiment, but what they wanted to do was compare the loss of water and nutrients from an uncut forest, which was a control site, which one had been stripped, which was the environmental site. This one right here, as you can see, is the control site where they totally left it. And what they tried to do is by stripping this, they wanted to really measure levels of nutrients that went down the hill and through the water systems, particularly drained through the eroded soil, to see if it really had an effect in our environment. They stripped about 30 to 40% of the land and increased in more runoff. So what happened is when it rained out, normally what happens is vegetation, like in this region right here, would hold that runoff. But in areas that have been stripped like this, and we'll do a case study later in the year in the region of the Himalayas, what they find happens is there's runoff, and when there's runoff, it takes all the nutrients with it. Much more dissolved nutrients came with it, and much more soil erosion with this experiment. So we'll kind of talk about that as we go. Within the scientific method, the first thing we need to do is identify a problem, find out what is known about the problem, something about maybe heart disease, cancer. Environmental problems are how to reduce the effects of acid rain, for example. We need to ask a question to investigate how do we reduce the effects of acid rain. A possible answer to that is maybe reduce the amount of output of something like SO2 from paper mills. Maybe we burn cleaner coal, if you will. Cleaner coal are things like anthracite instead of bituminous, something we'll talk about down the road. We perform an experiment over and over and over again. We collect data, we analyze the data to answer the questions, and finally, not finally, but the next step rather, propose a scientific hypothesis to explain that data. Next, what we do is we use the hypothesis to make projections that can be tested, and we test those projections. If we capture as much CO2 as possible, will that reduce the effects or the acid rain in the atmosphere, and of course the long-term effects of that? We test the projections, we accept or revise the hypothesis as needed, and eventually we can come up with a scientific theory. Definition of a scientific theory is something that's well tested and widely accepted hypothesis, and we'll talk about a little bit more soon. 4 important features of a scientific process. There must be curiosity. A scientist tend to be very creative. They think outside the box about possible solutions, about possible ways to solve things in general. There's skepticism from other scientists. You know, is that the case? Are you limiting variables? If you were to reproduce it again, the next one, will it occur over and over and over again? If you reproduce it in a different environment, will the same results occur? And of course, peer review is very, very critical, and you can kind of see a picture of that on the side. What happens is once a scientist goes through the experimental process and comes up with a conclusion, other scientists from around the world peer review it and make sure there's no sources of error or any problems with the experimental design. A scientific theory, as we mentioned before, a good example is the theory of dinosaurs. Now keep in mind, sometimes people say, well, theoretically this is going to happen, and really that's not the way scientists use the word. A theory rather, is rarely overturned unless new evidence discredits them. A theory is based on scientific fact. The theory of dinosaurs, we know they were dinosaurs. We found fossil evidence of dinosaurs. Scientific law, excuse me, it's even a further step up. What scientific law is, and the law of nature, is a well-tested and widely accepted description of what we will find happening repeatedly at the same way in nature. A very good example is the law of gravity. No matter what's going to happen, gravity is going to be there. We know that. Another good one would be the Newton's 3 laws. No matter what happens in nature, those 3 laws are going to be consistent. So that's very well tested, very widely accepted. It's been tested multiple times over and over and over again, and scientists have concluded. There is something called tentative or frontier science. That's kind of new science, not yet considered reliable in the scientific community. Maybe new experiments are going on. And keep in mind that a lot of experiments take a lifetime, if not more than a lifetime. People continue on experiments to see exactly what results may be. So frontier is kind of new. What's going on in the forefront? We've got that constantly going on with things like cancer research, again, heart disease research, which is a really good thing. Reliable research is widely accepted by experts, whereas unreliable science really hasn't been through the peer review, excuse me, or has been discredited. So we can throw that out and start over again. Now, there's no doubt science does have some limitations. Scientists really cannot prove or disprove anything absolutely. The beauty of science is what's discovered today may be different tomorrow. Maybe there may be a different discovery tomorrow. Scientists are not free of bias about their own hypothesis and results. As I mentioned before, lots of times science can take an entire lifetime experiments in order to prove, well, obviously you're going to build up bias against it. And that's part of the scientific community when we do peer edits to try to get those out. Systems in the natural world involve a huge number of variables and complex interactions, and that's what's real tricky. One thing that's out there is when we test a new medicine, and keep in mind that for a new medicine to come aboard, it usually takes about 10 years of research and trials. We do these what's called epidemiological studies where we give like 5,000 people the medicine, 5,000 people a placebo, and what happens is we see what the effects are. Well, the problem with that is everybody in the world has been exposed to different environmental factors. We all have a little bit different genetic disposition, different tolerance, different level of threshold and things of that nature. So it's kind of hard to always eliminate variables. Swinging over to a little bit more chemistry stuff we'll talk about in this class. Matter, of course, as mass takes up space. Elements can't be broken down really any further. They have unique properties. You can see to the right a couple elements there. The silver one is liquid mercury, which we know is a neurotoxin, and of course the one on the far right is actually gold. Compounds, two or more different elements bonded together in fixed. Here's a list of a few chemical elements we'll talk about in the book. Arsenic is a poison. We'll talk about carbon. Anything with carbon in it, of course, is deemed organic. Copper, I'll talk about copper mining. Chlorine, any pesticides that are heavily chlorinated tend to be very bad for the environment, bad for us. Lead is a neurotoxin. Mercury, another neurotoxin. Nitrogen, we'll talk about a lot. We'll do the nitrogen cycle, which is how plants get nitrogen, and then we absorb it, and just a whole bunch of steps to that you get to look forward to. Phosphorus is another one. Phosphorus is a huge limiting factor for plants, and it just goes on and on from there. Uranium is something that we use in nucleus. The atomic theory is all elements are made of atoms, of course. You learned about that in chemistry. Subatomic particles are broken down into several parts. In the nucleus, we have protons, which have a positive charge, neutrons, negative charge, and of course negatively charged electrons that orbit the nucleus. And we'll kind of break that nuclear energy a little bit more. Remember, the atomic number is the number of protons in the nucleus. That's also going to equal the number of electrons. Mass number is the number of protons plus neutrons in a nucleus. And that isotopes are something we'll really talk about when we do carbon dating and we talk about nuclear energy. Isotopes are same element, different numbers of, it should say neutrons here, not protons. Sorry about that mistake. Differ in number of neutrons. Ions are a net positive or electric charge. What happens is when an atom, in order to become chemically stable, gains or loses electrons, it becomes an ion. Acidity we'll really talk about when we do pollution. For example, water is generally a pH of about 7, unless we have a little chlorine added to it, that's about 8. Anyway, what happens when we get sulfur dioxide up into the atmosphere? It'll form a lower pH, which is of course more acidic, and it'll reach a pH of about 4, which has detrimental effect on our vegetation and definitely on our ponds, including our fish and all the living things that are in there. Couple more ions that are used in this book. We'll talk hydrogen ions quite a bit, aluminum. Ammonia will be a big one. Ammonia is NH4, and ammonia is going to come into play when we do the nitrogen cycle. Some negative ions. Nitrate is the favorable form that plants want so they can absorb it and process it. Sulfates, phosphates, remember the 8's ATEs that are in each of these: carbonate, nitrate, sulfate, phosphate. That's the ideal form that a plant would want to grow. Back to the experiment that we talked about originally, where we had the undisturbed land and the disturbed land. What the experiment provided was, back in the 60s, that if you look at an uncontrolled watershed, it's in the blue. What's happening is it's pretty stable over time, the level of nitrates that are discharged through the water, because the vegetation actually holds it. It doesn't allow those excessive nitrates out in this case. Well, what happens if we have disturbed land, which you can see in the red right here? What happens is, because we've cleared the vegetation, we get all those dissolved ions actually flowing down the system. And instead of being up here to help plants grow, we get it down here, and then we get that excessive nitrates forming downstream, and we get something magical called just bad. Couple compounds that we'll need to know: NaCl, salt, sodium hydroxide. Biggies are things like carbon monoxide when we talk air pollutants, carbon dioxide, the global warming agent. Nitric oxide is a biggie, nitrous oxide, nitrogen dioxide, nitric acid forms acid rain. Methane, water, of course, is a biggie. Hydrogen sulfide given off by swamps. Sulfur dioxide, sulfuric acid is a biggie. Ammonia is a biggie. And that's kind of the biggies that you really need to know in this class. We'll hit that down the road. Keep in mind, anything organic has carbon in it, at least 2 carbon atoms particularly. Hydrocarbons are a big word, because hydrocarbons, when you think of things like oil is a prominent hydrocarbon that we burn, and unfortunately we get excessive carbon in the atmosphere. Chlorinated hydrocarbons are something that tends to make up really bad pesticides. That's bad for us to inhale. Macromolecules, complex organic molecules, things like carbohydrates, proteins, nucleic acids, and lipids. Those are the macromolecules that we need to survive. You can see a little picture down there of hydrocarbons. One thing people don't realize is that plastic bottle right there is actually made up of oil, so without oil we would not have that. That's the end of part 1 for chapter 2.